All right, we're going to continue this time into the second period of Greek mathematics, which will lead through Plato and his school a little bit farther than that. I think we'll probably end about Euclid on this one and then move on after that. All right, so let's talk about where are we at? There we go. Democritus. Many consider to be the father of modern science. He was a famous atomist, um, though I guess at this point we don't have the word atom until he comes up with it. The theory of Democritus held that everything is composed of atoms, which are physical but not geometrically indivisible. That between atoms there lies empty space, that atoms are indestructible and have always been and always will be in motion, that there is an infinite number of atoms and of kinds of atoms which differ in shape and size. So he introduced the idea of an infinite number of points that make up the line. Uh, so this is where, matter can be changed but can't be destroyed or created because the atoms were already here. They were created here. So this is kind of that logic. Um, and then he observed that a cone or a pyramid has one-third the volume of a cylinder or prism, respectively, with the same base and height. So he observed this, and we get some geometry from him. Then we have Anaxagoras of Clazomani, Maine, Mini, Greek citizen of the Persian Empire during the Greco-Persian Wars, famed as the first to introduce philosophy to the Athenians. He was imprisoned for claiming that the sun was not a god and that the moon reflected the sun's light. Yep, imprisoned for stuff we know. Um, Now, we didn't at the time. He was credited with predicting the fall of the meteorite in 467. There was a meteorite fall in 467. He attempted to give a scientific account of eclipses, meteors, rainbows, and the sun, which he described as a mass of blazing metal. Okay, gas, but close enough. So what was going on? So let's look at where Greece is. You can see it down, where we at? Down here, right? And all of this is considered part of Greek. We have a lot of wars up here in Germany. They're all fighting each other. Um, we have the Achaemenid Persian Empire. That, of course, is growing, and the Greeks did fight with them. Uh, and that was very, well, that was one of the largest, most powerful empires at the time. You can see what was going on in Korea, the Mongols, uh, the Zhou states, which would be China, um, and the Tibetans and the Burmese and Thais and stuff. And then we have the Hindu kingdom and republic, the Arabs down here, which had some connection with the pastoral Saharan pastoral nomads. And then we had the West African people and Ethiopian farmers and stuff down there. Um, so a lot going on during this time. There was a lot of uh, infighting in a lot of these regions. The Italics, Etruscans were fighting with, but were considered part of Greek territory. But the Persian Empire, you can see, had gone all the way around and kind of had taken a lot of it. So we have Hippocrates of Chios, not Hippocrates of Kos, who's the father of medicine. He founded the area of lunes. Area of lunes, certain lunes are certain crescent-shaped figures, noting that the ratio of the areas of two circles is the same as the ratio of the squares of their radii. He tried to achieve the quadrature of the circle, which is a squaring of the circle, and he was the first to write an Elements of Geometry. And a fragment of this is embedded in the work of Simplicus. So while Thales had written an Elements, it wasn't an Elements of Geometry. Hippocrates wrote an Elements of Geometry. which we'll see again. His is the first one that we know of. There could be others. And then we have Plato, was a philosopher and a writer of philosophical dialogues, a student of Socrates and the Pythagoreans. He was the teacher of Aristotle, founder of the Academy in Athens, which is the first institute of higher learning. This would be the first university, maybe we might call it. He may have studied under the mathematician Theodorus of Cyrene. We get that from some he uses a reference to a mathematician, Dietius. Uh, and Plato was not a mathematician. He was considered an accomplished teacher of mathematics, but he didn't consider himself a mathematician. He considered himself a philosopher, though the two are interrelated, I think. Theodoxus of Cnidus, one of the greatest mathematicians in classical Greece, was his student and wrote most of the book 5 of Euclid's Elements. His cave analogy that has been pictured in the Renaissance. Here, you have a picture from the Renaissance. Uh, and the idea was the uneducated masses were in the dark cave, and the educated mathematicians, philosophers, and politicians were in the light. Uh, he distinguished between pure and applied mathematics by widening the gap between arithmetic, that now would be called number theory, and logistics, which would now be called arithmetic. It's interesting how the two end up in different places. In Plato's divided line, mathematics falls under both the highest form of true knowledge and the second highest form of true knowledge. So we're clear, Plato believed that everyone should come into the light. He wanted them all to come into the light. He wanted everyone to be educated. So this portrayal, you could say that these two here right at the edge are inviting these others over to the light. He felt that education was important for everyone. The Platonic solids, these come from him, his name, and these are associated with each of the four classic elements, with a regular solid, cube, octahedron, icosahedron, and tetrahedron. The fifth regular solid, the dodecahedron, was the element which made up the heavens. So one was air, fire, water, earth, and then one were the heavens, the space, stars. Yes, these are, it's kind of funny. These were dice to tell your fortune, to give you a sign of what was happening. Yes, these were made as dice. That would be like fortune-telling dice or something. Isn't it interesting that these are the primary shapes of the role-playing game Dungeons and Dragons, that was created in the early 70s, mid 70s. And they, Dave Arneson and Gary Gygax had decided to use the Platonic solids for shapes of dice. These were not new, but they made them numbered dice to tell stuff. So I feel like it's interesting that those were used, 2,000 years beforehand are now being used again. And of course, it's had a resurgence. Aristotle was a Greek philosopher and a polymath. We've talked about polymaths already, though he's one of the early ones. He was a student of Plato and a teacher of Alexander the Great. Base of mathematics is logic, but the nature of mathematical relations is completely specified by postulates that dictate the physical experience. So it's interesting. He took a very both almost spiritual and human relationship with them. So the base of mathematics is the logic, that nature that is completely decided. And then the relationship, though, is based on our physical experience. He argued that a capability like playing the flute could be acquired, the potential made actual by learning, which makes him, in my mind, this ideal teacher. The idea that anybody can learn anything, uh, it just takes practice. It takes learning about the instrument and or the subject, and then practicing it. And I feel like that's something that we strive for with our students. His logic system, all humans are mortal. Minor premise, Socrates is a human. Conclusion, Socrates is mortal. This is one of the oldest ideas of the logic that happens. Aristotle's immanent realism means his branch of philosophy is based on the study of things that exist or happen in the world and rises to the knowledge of the universal. Where Plato's philosophy begins with the knowledge of the universal forms or ideas and descends into the knowledge of particular imitations of these. Aristotle uses induction from examples alongside deduction, where Plato relies on deduction from a priori principles. And if you don't know, a priori is knowledge. Knowledge is that which is independent from experience. It includes mathematics, tautology, and deduction from pure reason. This is the idea of knowing something is true because you read a proof that something is true, but never actually applying anything that uses that proof or uses that property. And then that's a priori knowledge. You know it independent of use. I know the sun is hot, right? I know that from all a priori knowledge. I've never actually experienced touching the sun. I have experienced the sun. I live in Phoenix, right? So mm, maybe that's not a priori knowledge. You get the idea, though. This is actually like, oh, this is true. I don't have to touch it. Uh, Aristarchus of Samos, he was an astronomer and a mathematician, first known heliocentric model that placed the sun at the center of the known universe. So he walked through it, came up with this plan, this knowledge. The Earth revolved around the sun once a year, rotating about its axis once a day. He influenced by the concept presented by Philolaus of Croton of a fire at the center of the universe, but identified that central fire with the sun. Put the other planets in their correct order of distance around the sun, not necessarily the correct distance, but the correct order. Like Anaxagoras before him, he suspected that the stars were just other bodies like the sun, but farther away from Earth. A weird thing, at this point, we're not calling Earth Earth. Like I'm using that terminology, but he would have never used that word. In fact, that word hadn't been used at all. At this point, he is referring to it as Gaia or Gi. That was the name of what we call Earth. In fact, the word Earth is not that old. It was Gaia for about 6,000 years, Gaia or Gi, depending upon how you pronounce that and from where. That was the word for the earth for 6,000 years. Okay. Um, at the time of his life, 6,000 years prior, it had been called this. So Earth is funny. We will call it Earth. Uh, in fact, we're at a weird point where we're going to start calling it Terra at the same time that we're going to call it Earth. And I'll mention why that happens as we get to it. We have Euclid, Euclid of Alexandria. He's best known for his treatise on geometry, which is called The Elements. And this influenced the development of Western mathematics for more than 2,000 years and is still. In fact, I teach from Euclid's Elements in my higher geometry class, at least the first third. He was a pioneer of axiomatics in geometry, which is proofs, or not proofs, is truths, axioms, basically, that we use in most studies of mathematics. These are foundational, and theorems are based on axioms and definitions, or postulates and definitions. Uh, Fundamental work in the field of Greek mathematics. The first edition of the translation from Arabic into Latin was in 1482. I should mention that this book was more well read than the Bible until the Renaissance. So this was more read than the Bible from when it was written until the Renaissance era. So about 1600. Okay. Why am I making that point? Because technically at this point, the Bible's not written. We don't have, well, this is a little bit after Moses would have gotten out of Egypt, right? So the first books of the Bible are written by Moses, and we don't have much of that yet. So we certainly don't have all the rest. And this is before Christ, so we don't have Jesus living, so we don't have his and his disciples' works, books. So written about 300 BC, this is a textbook that includes number theory, the Euclidean algorithm for finding the greatest common divisor of two numbers, arranged in order many of Euclid's theorems, perfected many of Theaetetus's theorems, brought to irrefutable demonstration the theorems only loosely proved by his predecessors. Ptolemy once asked him if there were a shorter way to study geometry than the elements. In his aim, he was a Platonist, being in sympathy with this philosophy, whence he made the end of the whole elements the construction of the so-called Platonic figures. How does it start? Well, the elements begin with definitions and five postulates. There's also axioms, which Euclid called common notions. A common notion would be things which are equal to the same thing or equal to each other. These are not specific geometric properties, but rather general assumptions which allow mathematics to proceed in a deductive science. And his first five postulates are these. A straight line segment can be drawn joining any 2 points. Any straight line segment can be extended indefinitely in a straight line. Given any straight line segment, a circle can be drawn, having the segment as the radius and one end point as the center. All right angles are congruent. And then, if two lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than two right angles, then the two lines inevitably must intersect each other on that side, if extended far enough. This postulate is equivalent to what is now known as the parallel postulate. It is the parallel postulate, though not how we tend to write it now. His fifth postulate cannot be proven, though many people have attempted. In fact, that will actually be the deciding factor in other geometries. Euclidean geometry is flat surface on a board or a screen, but the world isn't flat. So keep that in mind. Euclid used only 1 to 4 of his first 28 propositions for the first 28 propositions of his elements, but did invoke the parallel postulate on the 29th. And in 1823, Boya and Lobachevsky independently realized that entirely self-consistent non-Euclidean geometries could be created in which the parallel postulate do not hold. That works. That works for us, talking about geometry and talking about the world we live in. Our world is non-Euclidean. If I look at the equator and I look at the longitude lines and I draw them up, they will intersect the pole at a particular degree. And depending upon my choice, you can see some that are drawn here. This is one drawn 90 here, intersecting at the equator, 90 here, intersecting at the equator, and this intersects up here at the pole at 50 degrees. So 90 plus 90 is 180, plus 50 is 230. So this triangle has degrees of 230. If I'm looking flat, like on in the small scale, you can see I create a 90, a 40, and a 50, and this is a Euclidean. So non-Euclidean are world, but on the small scale, we can still go Euclidean. So given a line and a point not on the line, it is possible to draw exactly one line through the given point parallel to the line. This is the parallel postulate. Spherical geometry is just as real as Euclidean geometry, but the theorems and general results are very different. Same is true for hyperbolic or any of the other geometries. There are quite a few results from Euclidean geometry that are completely false in spherical geometry, and vice versa. So we need to be careful. The other thing that he gave us was the GCD algorithm, so also called the Euclidean algorithm. If we have to find the GCD of 1071 and 462, this means we're going to find the greatest common divisor. Now, many of you would be like, well, you need to find all of its factors, which could be true and would work. This algorithm doesn't necessarily do that. And it works like this. We do magic. Let me throw it all in there. So I take 1071, I subtract 462. It's big enough I can do it twice, so I do it twice. That's going to give me 147 left. So 1071 is made up of 2 times 462 plus 147. Then I take that remainder, that 147, and I subtract that from 462. I can do it 3 times. 1, 2, 3. I get a remainder of 21. So 462 minus 3 times 147 plus 21 equals 462. Okay. Then I have that 21 remainder. So I can subtract that from 147, right? I'm subtracting this from the previous remainder. 147 minus 21, minus 21, minus 21, minus 21, 21, 21, 21. I get to do it 7 times and then I have no remainder. So 21 works evenly 7 times for this remainder. This means 21 is the largest common divisor. And you can kind of think of it as replacing this 462 here with 3 times 147, right? But then I have a 147 here, but I'd have the 21 remainder. So then I can replace the 147s here, which are part of this now, and here with 27 times 21. So 21 will divide all of this, including 462 and 1071. 21 is the largest, greatest common divisor. So that's pretty cool. So compared to Mesopotamian and Egyptian mathematics, Greek mathematics used proof, logic, and demonstration. This was much less practical in its orientation. Was definitely more geometrical and less arithmetical. Was considered good for the mind and the soul. What about sources? Well, there's no primary sources remain. Though we have found the remains of a book by Archimedes, which we haven't talked about yet. He's in the third. We will talk about him in the third period. Secondary sources or worse, so mainly mentions in books written much later. So that becomes a problem when you don't have direct sources. And some fun. What my friends think I do is calculate. Uh, what my family thinks I do is compute. Society thinks I do something like out of a brilliant mind or something. English professors think I do magic. Uh, I think I do something like Einstein. Nah, no, I don't. But I do something I feel that's fundamentally important. Um, what I really do is a lot of frustration, a lot of crumpled pieces of paper. So some of these are kind of fun. All right, that's it for this. And then we'll get into the third of the Greeks in just a moment. Okay, let's talk about the third period in Greek mathematics. This is the Alexandrian school. It flourished in what we call Greco Egypt.